Hello and welcome to the Exam Review 3 review session. Whee! I didn't get any responses. How was everybody saying? Anybody respond? I thought it was rhetorical. Good. Okay, good. There, good. See, you're all right. Yeah, Samantha, you're okay.
I'm here.
You're here?
I'm here.
You upset?
No,
Life is getting you down.
no, I'm just so ready for this semester to be over.
I hear ya.
I mean, it went a lot faster than last year's. Oh, that was horrible. What Kelly was going on and on and on. But
Life will get better.
yeah, I'm ready to move on.
I hear you. So what we covered since exam 2, we've done chapter 15, where we've done angular kinematics, velocity analysis, and acceleration analysis for rigid bodies. And I have if you don't have your own, you need an equation, if you have an equation. Oh, okay. You make airplanes out of it. I think we just covered lift or fluid mechanics. I thought we should make one of the home problems should be airplane, big airplane problems. And but anyway, this is the section that we're going to be specifically using for the exam, and I have a bunch of old exam problems. Usually, I end up going down the list. I guess our list isn't really that long for this, but we have a kind of subtopics as part of here. The velocity analysis we want to be able to do, and the acceleration analysis. We want to be able to use a vector approach, a 3-diagram approach, and then for the velocity analysis, we want to make sure that we can do an ICR. So that's probably what we want to try to cover today, is to try to get some of those problems in. And what I'd like to kind of do maybe is, instead of using the older Coast Guard Academy exam problems, which these are, I want to leave these for you because we have the solution. Have I posted the solutions already? Anybody notice? Let's check. Let's see.
Trying to keep my head above water.
I hear you. Hey, no judgment on my part, right? I mean, I totally understand. If you haven't looked at it yet, that's cool. I hope I don't come off as a judgy person. Here you go. I haven't released them yet. I don't know. I still kind of want to try to dissuade you from the temptation to just look at the solutions, but maybe I'm going to just go ahead and let you make that decision on your own. If you haven't figured it out yet, it's really important that you don't just look at the solutions, that you try out problems. And I also thought perhaps that instead of going over these problems, I might try these from this Missouri University of Science and Technology. Now, I have posted those. I'm not sure if anyone gets a chance to use them. Maybe you already have so many resources that you didn't ever bother to look there. But not only do I have some that I just selected and thought, hey, these might be good problems for you to try out. You can go to this to their website, and this Dr. Ralph Fleury's old exams. It's been kind of dormant for a while. I think it's 2005. You see, probably, so it's been a long time, 1999. These are old exams. When we say old, we really mean old now at this point. But they are kind of like an idea. This is Jeff Thomas's previous exams. These are nice resources to have. I wouldn't say, I don't like some of their solutions to these. They're a little short, a little too short, and don't necessarily go our way. But at least we have the answer, right? And can work towards it, and maybe give us that little clue thing that kind of like goes, oh, I got it. And I think there's a lot of benefit to quantity sometimes so breadth instead of depth when it comes to exam preparation. Like, you don't need to solve the whole thing all the way through. You just need to get past the thing that you need. And often for people, that's the problem identification. Like, what is it? What is the gist? What's the little thing that's going on here in this type of problem? So I was thought maybe by way of using some of these, which I separated out just a couple minutes ago, into individual ones instead of so we would just kind of take a look at a problem like this. Let me see if I have which one this is for me, so I can, because it's tough to read it off of the off of the board at the same time as looking down here, we can identify this problem. So let's just read it quickly and see what we have to do. And maybe we want to try, when we can, to do some of these a couple different ways, right? Just to double check ourselves, to see what might be different in this situation from what we've seen in previous problems. So the first thing that I would do is maybe I want to check this with ICR, right? Test our ICR skills right away. So please, if you can, like I'd let you know, you don't have to, but it'd be great if you could get paper out and try stuff out today. If you need more paper, I can go grab some off the copier. If you just don't want to waste any of your other paper. But how would you do? How quickly can you find an ICR in this right here? Yes, sir.
Pretty quick, right?
Yeah, because
Because you're gonna have the accelerations going like one normal and then the tangent one.
well, I don't know if you're using the word acceleration. So
But the velocity is gonna be this on that same tangent as the tangent acceleration.
I got you. Yeah. Well, I just.
A is fixed point, so B is
B would
only
be where
over
your
rotate.
velocity would be.
Circular, so the velocity of B is tangent to its path.
Mhm.
You use that, and for BC, you would find your 90-degree angles.
Yeah. Well, what I would say in here. Let's see. I'm sorry. Let's see. Come back to here.
I'm glad you and I had the same thought process.
So one thing I don't like about this particular figure is he's not really quite to proportions, or maybe he's not too terribly bad. I don't know. Where we have here, and this is we're told this is 30 degrees, and so this is I didn't do too bad right there. This one's at 60 degrees, so it's going to have it's a very similar thing. But let me see if I can. I think I'm going to exaggerate just a little bit right there. And so that was B, and then we're going to have this guy right there. And so here is the motion is coming down at omega AB, that's A, is 4 radians per second. And the lengths of this, they said this is 200 millimeters. And this was 150 millimeters. And then they also gave the angles here. I often have a problem that I don't remember to look up and see where this is on there. So with that,
Show the question one more time real quick.
sure. This is from MUST, the Missouri University of Science and Technology. I think they must have decided to name their school that, so they would spell an acronym. That's my guess. I think. So anyway, let's see this. C. So really quick and dirty, how would I go about this? Well, one thing is I know is that the line for any fixed rotation thing for the ICR is going to be in line with that link. And then this guy has to go left or right. So boom, I just found the ICR. And because I saw that the velocity is going to go that direction, right? We know that's what the VB is going to be. So I like to draw the link out to the side. And he's moving there with his omega AB. Therefore, his velocity of B has to be right here. And we can get if we needed to, we could get his angle by drawing it carefully and seeing that this angle, which is given here, it must be the same one as that. So that's going to be 60 degrees. And that VB is going to be omega AB times, I'll call it LAB even though they didn't label it. So it's simply going to be 4 times 150. So let's stick with millimeters. I wish I brought my calculator with me, but I I got my phone. And so I should be able to do 4 times 150 in my head, but I did it anyway. 600 millimeters per second. And with that, depending on whether we're going to go ICR or we're going to through diagram methods, let's stick with the ICR for now. I drew it on top of this, but I really prefer to, like, it's my own preference. And even when trying to solve one, I kind of would like you to kind of like make it over to the side and redraw it instead of trying to draw on top of the thing and getting it all cluttered. Right, so we got that this was the velocity B. So it's going to be RB with respect to ICR. It's going to be RC with respect to ICR. And we could tell because of the direction of VB that this omega BC must be going clockwise. And therefore, this VC must be going to the right. So now we just got to get a little bit of, do a little bit of geometry to figure out, first off, what the angles are. So we can see from right here that this angle right there must be the complement of the 60, right? Because one way we could do this, we could see that that's going to be 60. So this one must be 30 degrees. And we were told this is 30 degrees right here. So this must be 60. And the same true for that. This must be 60. And then you could do this in a couple different ways, but you could we'll come to the conclusion that this must also be 30 degrees. And we've encountered a problem similar to this before, right? Where we had a 30, a 120, and a 30. And we remember that this length must be the same as this length, right? Because it's got equilateral, yeah. One of those two words. But anyway, so we know that RB with respect to ICR has to be equal to, let's call it length BC, which is 200 millimeters. So omega BC must be equal to VB over that, or 600 divided by 200, and we get 3. I think I did it right. And then we can find RC with respect to ICR in a couple different ways. I think there's an easier way, but I'm going to go ahead and use the law of sines and just say that the RC with respect to ICR divided by the sine of the angle opposite, which is 120, is going to be equal to LBC divided by the sine of 30. Because they're opposite from there. So we would say that RC with respect to ICR is going to be equal to that 200 times the sine of 120 divided by the sine of 30. So we get 346.4 millimeters, and therefore the velocity of c must be omega bc times r c with respect to ICR, or 3 times 346.4, 1,039 millimeters per second. So from the original question, that's what we had. So for as a means of compare and contrast, I don't know why I'm writing diagonally here. Let's go to the 3-diagram method. So we can already start with what we had up above. Up here, we could have made this same diagram up above and recognize that this, we had that value, and that this thing is going to be, let's call it 30 degrees below horizontal from the arrangement that we have. From a careful diagram really helps that out. And by the way, when Missouri, the Missouri University of Science and Technology, those problems, they call the 3-diagram method really the relative velocity method, is what they're saying up to the thing. And sometimes people do that same thing with triangles, by the way. So the 3-diagram, what we put into there, would be specifically for the only link that's both translating and rotating, and that's going to be link BC. So we're going to say, we know that the velocity right here at this spot is VB. And we know that this has to be horizontal. We draw that in there. Is that really out of focus? So I have another camera that I think is a better camera. All right, well, so this is the translation diagram. And so we put the known velocity VB onto both spots. And since this was the reference, it gets pinned. And now we know we're going to have a velocity that's tangent to that. Let me go ahead and, even though I know it's not true, assume BC is counterclockwise and draw that right in there. This one's a little, maybe, I wouldn't say easy, but there's sort of a simplifying assumption that kind of gets made right here because they told us this was 30 degrees right here. It's kind of easy to see that this right here is also 30 degrees. And so this is going to be VC with respect to B. And we know that the magnitude of C with respect to B is going to be equal to omega BC times L BC. There's no real reason to have this clipboard in here. Okay, I'm sorry. Thank you. So I will try to squeeze it all in there. The big idea when doing this 3-diagram method is we're going to try to find the velocity of C by taking the known translation and adding the velocity of C with respect to B, the relative velocity to it. So we've experienced a few of these where we could see, well, if a good strategy which is our main goal when doing this in this situation, is to find out omega BC. So we can eliminate stuff on the left-hand side that we don't know, right? Because we want to know the velocity of C is our main guy, but he's going to be 0 in the y direction. So breaking this down into the y component, we could say that it's going to be 0 here. I should have drawn this out right here. So I went, this was 30 degrees. And this guy right here, we know his magnitude is 600 millimeters per second. We got it previously already. So that's how previously works, it's that it happened already. And we notice that it's negative direction. So we have the 600 millimeters per second, but only in the y direction. So we're going to take the sine of 30 degrees. Over here, we're taking, now this is the relative velocity right here. And as I've drawn it, because I chose to guess it was going to be in the counterclockwise direction, the result of that is a negative y direction, which is going to be omega BC times the length of this thing, which is what, 200? But you got to remember, it's only the y direction, so you need to take the sine of 30 right here. So our conclusion is that we get omega BC is going to end up being negative, and you can see that the sines are going to cancel out, so it's pretty easy to see that we're going to get negative 3 radians per second. So it wasn't going in the direction that we thought. Sorry, here, let me move this back up. And then we can go into the x direction now. And we'll just take VC as being, assume it's in the positive direction, and write out the x direction for right here, which is going to be it's positive, right? So we see it's going to the right, it's positive. So it's going to be that 600 times the cosine of 30. And here, let's draw what the arrow is, but for what the situation is, which makes it look like it's going to say, well, it's going to be negative, but we know that it's going to be omega, and we know that omega is negative, right? That's my way to, I don't bother to update my diagram. I just go ahead and put in the value that I know onto there. It's going to times 200, and now that's going to be the cosine of 30 as well. And we should get the same thing. So 600 times the cosine of 30, which is 519.6, and I think you're going to have the same thing. You're going to have 16. You're going to have also 600 times 30, so it's really times 2. So we end up with the same thing, a 1,039 millimeters per second.
Is this about as detailed as a question that you could expect on the test?
I think so. That's the reason why I kind of picked some of them out from Must. I mean, it kind of, you know, the exam is supposed to just demonstrate that you're able to do the problem. But there's like a whole variety of different, you know, different ones that you could go through. I probably wouldn't ask the ICR and this on the same problem. And I might even just make ICR. I might draw like 3 or 4 things and show the ICR, and then don't solve it. So should you be able to just do those fairly quickly? I should only say like something like 4 because it would be unfair to get it wrong, and then because you just made a simple mistake, and then it to be a big chunk of points. So, you know, just talking about trying to make the thing a fair measure. Let's do some more though. These are pretty straightforward here. Here's a 4-bar. And they said use the instantaneous center of rotation for this, but that might be a little easy, maybe. Yeah, I think that might be a little too easy. Can anybody tell me right away where the ICR is off of this one?
It would be like right in the middle of PC.
I think it would be exactly at D.
Mm-hmm.
Can you see why that is? For 4 bars and for others, you could just extend the legs and see where the extent of their legs intersect. And in this case, the only place they can land is at D. So let's see, let's try to prove it to ourselves as skeptics. I think it's a healthy degree of skepticism is a good engineering trait. So let's see, here's the problem. I'll write it out next to it. So we have link AB, no, I guess it's E and B. And this thing looks like it's probably at a 45 degree, yeah, it says it's a 45 degree angle. And if I drew it correctly, but I probably didn't. Yeah, I didn't make it. I didn't really make it to the correct proportions right there. Well, there's a little bit of difference. Let me see. Yeah, they didn't give you the length of this right here. So there's really just a little bit of a geometry thing going on. And I really wish I had done just a little bit more care in getting the proportions of this just right. Because this one here is 4 inches in between there and there. And see, that's called, this is B right in there. They tell us this is 45 degrees. Therefore, we know that right there is also 45 degrees, by the way. And they tell us this is 2 inches right up here. And this, we'll call it omega BE, is 5 radians per second. In itty bitty words right there. And this is point A. And I think that's what we're trying to find is A. And this is C, and this is D. But maybe just redrawing this part out right here just a little bit bigger. We could see, well, first off, let's draw BE separately. So here's this. We know he's going this way, so we know that the velocity of B has to be equal to, sorry, let me pull this back over. There you go. Velocity of B must be equal to omega BE times its length of BE, which is going to be 5 times 4, and I could even do that. It's going to be, whoops, 20 inches per second. Well, putting it onto this link right here, we also have, so we know that's going to be VB. The location of this velocity must be right here. Looking back up to here, the velocity of at C must go left and right, so it has to have the coming down between there, and that's what forces the ICR to be right here. And we'll note that that means omega, call it BC, must be going that direction. And this is R B with respect to ICR. And right here is our C with respect to ICR. But we don't really care about that because I believe that the problem was asking for point A. So coming back to the original problem here, we can identify that this length between B and D must be 5 inches, right? So the real thing that we're going to want to get is this right here, which is going to be, RA with respect to ICR. So RA with respect to ICR. I think the easiest way to find this is to take that 2 inches. We know this distance right here is 2 inches. So I'm going to say it's going to be equal to 5 plus, that's the hypotenuse, so 2 times, and let's get it right because that's 45. That's going to be the cosine of 45. So it ends up being 6.414 inches. And so therefore, and we can draw it onto there. You can have the velocity at A. We, while we're here, we might want to go ahead and get this angle right there, because that's going to be the same angle as this one right there. So I'm going to call it beta. Don't use beta enough. And let's see. Do it a couple different ways, because we already got the hypotenuse. No, we already got the hypotenuse here. Oh, did I just screw that thing up? I think I just screwed this up, by the way. I apologize. Let me come back. I was wrong. What I just found right here was the horizontal distance. I just found that horizontal distance. So this is not true right here. Well, let me erase this part. I'll keep that 6.414. And let me just call this, I'm just going to call it X for right now. What I mean is that's the distance X right between there. Or I might call it AD, right? That's the distance between A and D in the X direction. And we could go YAD. And that's just going to be 2 times the sine of 45, but obviously that's the same thing that we just got right there, which should be 1.414 inches. So RA with respect to ICR is going to be the hypotenuse of that, 6.414 squared and 1.414 squared. So that ends up being 6.568. And then the angle, which I was about to call beta, and that's what triggered my acknowledgement that I made a mistake, is that as I went to go look at the angle, I was like, oh yeah, This first thing I did was just find that that was 5 plus whatever that was. So now we have rise. I'm going to go rise over run, which is going to be the 1.414 over the 6.414. Taking the inverse tangent. We end up with this small angle, 12.43 degrees. So the velocity at A is going to be that omega BC that we got before, right? Where did we get? We wrote. Did we write it anywhere?
Yeah. At the bottom of the diagram, it says omega BC at the bottom corner.
Right here.
Yeah.
Okay, but we never figured it.
Is it that up there, the 5 radians? Is that the...
Yeah, that was just VB, right? So we never got V omega BC was going to be VB over R B with respect to ICR. So that was that distance right there. So we found that it was going to be 20 inches per second divided by 5. Okay, that makes sense. All right, so it ends up being 4 radians per second. So using it down here, we wanted to go BC and go R A with respect to ICR of 4 times our 6.568. So we end up getting 26.27 inches per second. And we want to answer this in the standard way, which is to refer to the horizontal. This right here, this angle is actually from the vertical. So we need the complement of this right here. Yep. 90 minus beta is going to be 90 minus 12.43. So that's a 77.57 degrees. So when answering this properly, we're going to say the velocity of A is going to be 26.3 inches per second. And it's going to be in that quadrant right there at 77.6 degrees. That really looks out of focus to me. A little better. Wish there was like a light on this thing that was like shadow, its own shadow. Wishes. And we don't necessarily have to do this in the other way to demonstrate it, but I think it's a good problem on one level. It's just, kind of different from what we've seen before. You guys are so miserable. I'm so tired. I'm so tired. I don't want you to be tired. I want you to be, I want to energize you. I want to inspire you. Just not possible. I got it. Okay. I don't want to beat up on you. I got it. I got you. Let's pick something else. We got an acceleration problem. Oh, no, this is actually almost identical to one of our examples in class, except that the angles are a little weird. Here's a hard one. I'm kind of surprised that he asked this one. That to me seems like it could take a long time.
You're not gonna ask him.
I don't know. Maybe it's going to surprise me and be like really easy to do. Maybe there's a trick. Gave the angles and stuff.
Okay.
All right. I'm going to do an acceleration one. Maybe we'll find it. You want to find an easier acceleration one? Some of these will look like really familiar here. Let's see. We can do other ones. I don't care. I don't have an agenda.
Give 3 problems, the 3 test problems.
You're trying to use Jedi mind trick, but you have to appreciate I don't have a mind.
You're teaching us.
I don't know. Well, you know, it doesn't mean I'm like I know what I'm doing.
You know,
There's plenty of that. There's plenty of that going around. There's plenty of that going
You
around.
got a point. Definitely.
Yeah, there's plenty of that going around. Just trying to find. I don't see any easy ones, so let's just go to the hard one then. Trying to find an acceleration problem that's not terribly difficult to do. Let's do this one right here. I don't know if I made this one into a big one yet. Relative velocity, instantaneous center. Determine the acceleration point A. I like this one. Let's do this one. Most of the acceleration ones are a lot easier if the thing that you're looking at doesn't have, if the initiating body, in this case the wheel, isn't also an acceleration. If that one moves in a constant angular velocity, it makes it just a little easier, but not incredibly easy, but still a little easier. All right, so this one is like 2 feet tall, and it looks to me like they purposely drawn. Yeah, they didn't even give you the dimensions, so they must mean that point B must be aligned with. I guess we'll call it 0 because they didn't give us a letter for it. But they must be in line with each other, and it's at a 45-degree angle. I think 45-degree angles make it easier most of the time, or at least you could get it wrong without realizing you got it wrong. Okay. All right, and then this thing is moving at omega 3 radians per second, and this thing is 1 foot in radius right here. 1 foot, and they labeled that B, and they never labeled this other guy right here. So I don't know. I don't like O. I'm going to label that one D. It doesn't really matter, right? It's alphabet. It's just the alphabet. Boom. Right? So these guys must be in line with each other, and we're trying to find the acceleration at A. So first, whoops, all bendy and stuff. Actually, maybe I'll turn it this way because it's a little easier for me. There you go. So we want to find, we have to do a velocity analysis first to be able to find the acceleration. That's not too terribly bad. I'm going to draw the wheel by itself. Almost a little Tennessee twang right there. Just, I don't know if you notice. By itself. Unless it's Greenville, Tennessee, then it's a question. By itself. Everything's a question in Greenville, Tennessee. All right, so this guy is moving at omega, I guess we're going to call him BC. Let's call him BC, alphabetical order, BC. So his velocity is going to be down. So velocity B is coming that way right here. And it's just going to be 3 radians per second times this distance, which is 1 foot. So that's going to be 3 feet per second. Gotcha. While we're here and on this diagram, we'll take and go the acceleration of B
right? And now this is actually the acceleration of B with respect to C in the normal direction. So that acceleration of B with respect to C in the normal direction is also equal to the acceleration of B, which is entirely in the x direction, and that's going to be omega BC. I don't know why I didn't go BC right there. BC times the radius BC, and so that's just going to be.
That's not on camera.
Oh, it's not. I'm sorry. Thank you. So this is going to be 3 squared times 1, or 9 feet per second squared. All right, continuing on that. So that was just a little side trip there to get some information we know we're eventually going to need to know. Let's keep going with the velocity analysis. And so if we take a look at this link right here. All right, so first, well, we could just draw them and see where they intersect. Let me think here. Let me think. So this one's coming that way. And oh, okay, so this made it really, this did become very easy. These throw me off sometimes when you take a look at them. Yeah, okay. So here's the velocity of this, but here's has to be the direction of this guy right here. So here's the velocity of B. And if you take a look at link, what I called AD, its velocity has to be in that direction right here. So actually, once again, just like that other problem, the ICR ended up being right there at D. Do you see that? And it's hard to tell because it's sort of deceptive because they drew a wheel, but this is really a 4-bar, right? This is this link, and they're connected by this coupler. So right here is going to be the RB with respect to ICR. And right here is going to be the RA with respect to ICR. But notably, let's see, where they give the dimensions onto this thing. Yeah, they told us this is 2 feet, and I never labeled it. So if that's 2 feet, this RB with respect to ICR has to equal RA with respect to ICR, right? This guy right here is the length of AD. So since this is 45 right here, those legs have to be equal to each other. So we're going to have our omega AB. I guess that's how I labeled it, the AB, right there. And for this, we're going to have VA. Well, this is going to be kind of a little too easy. Our B with respect to ICR is going to be equal to our A with respect to ICR, which is going to be equal to 2 feet. So omega AB is going to be equal to VB divided by, I'm sorry, R B with respect to ICR. So we're just going to have 3 feet per second divided by 2, or 1.5 radians per second. And it's going to be ridiculous to write this, but it's okay. VA is therefore going to be equal to omega of AB times RA with respect to ICR, but it's a little obvious right here that that's just going to be 1.5 times 2. So that 2 is going to be 3 feet per second. And then even sillier, I'll write it over to the side. I'll draw it over to the side over here. That this link right here with VA, this is D and this is A. This 2 must have an omega AD, and that omega AD is going to be equal to VA over LAD, which is going to be equal to 3 divided by 2. And so this one as well is also 1.5 radians per second. One key thing here is we don't know the tangential, we don't know the angular acceleration of AD, but we do know its normal acceleration. It's going to be down, right? So the acceleration of A with respect to D in the normal direction is going to be omega AD squared times LAD. So that's going to be, we just found that, a 1.5 squared times 2 and it says, this says it's 4.5. I'm gonna double check that. 1.5 squared, yep, 2, yep. And that's going to be inches per second squared. That's going to be in the vertical direction, straight down. So I think we got all the information we're going to need to move on to the three diagram method acceleration. One thing I never got was the length of this bar. So let me get the length of AB. It's just going to be, well, we could do it a bunch of different ways, but it's just going to be square root of 2 squared plus 2 squared. So it should be what, square root of 8, right? Or 2.828. I mean, that should be familiar, 0.828, because it's a multiple of 0.707, right? Okay. And so my 3 diagram method here. It's going to be a little easier because of the 45 thing, but let's try to pretend like it's some other angle so that we can get the thing right. So here we're going to have the entirety, we're going to know all of the accelerations at B, because it's the wheel's moving at a constant angular velocity. Therefore, the entirety of B is actually going to be that 9 feet per second. Did I say inches somewhere? I probably put inches somewhere. Probably in a couple places. At least here, it should be feet. Yeah, I can say I did it. I only messed it up once. Okay, that's supposed to be feet too. Sorry about that. And we do know this acceleration right here. We have that value. We call it A, acceleration of A with respect to D, normal. So we're really trying to find this last portion of it right here from this. So as we've done before, if we know something fully, we'll use that as the translational, acceleration of B, and then pin it there. And then find this portion. Okay, keep in mind that there's going to be a component in this direction as well. We don't know the angular acceleration here, so we're going to go, this is AB. And so I'm going to assume it's in the counterclockwise direction, so that's going to make this guy. And this plus sign really keeps wanting to get in my way. Well, one of us is in the way of the other one. I don't know which one. You could blame me, either one, either guy. We know all those are 45 degrees. I think I'm going to go ahead and label this one even, and then use that as the basis for all the other stuff. I'll even call that one 45, because if this thing was known, that angle right there would be the same one as that, and the same one as that right there. So we're going to just try to keep consistent in trying to be careful with those angles. This guy is the acceleration of A with respect to B in the normal direction, and he is the acceleration of A with respect to B in the tangential direction, and he's alpha AB times LAB, and he is omega AB squared times LAB. So in this instance, for writing out the equation that we want to have here, A with respect to B tangential plus acceleration of A with respect to B in the normal direction. I think it's going to be in the best interest to go in the y direction because we know this value right here. A lot of times we'll have a problem where, you know, we're able to cancel one out because it's 0. In this case, we're able to take advantage of the fact that we already know the one. So we go the y direction here. So we take negative as drawn. That is going to be that 4.5, right? Negative 4.5. Acceleration of B doesn't play any role in that. Whoop, it's supposed to be an equals. Tangentially, we're going to say that we have, it's going to be also negative, and it's going to be alpha AB times the length of AB, which we know is 2.828. But we want to be careful and only use the part that's in the y direction. So we need to take the cosine of 45. We're also going to be in the negative direction here for the normal acceleration. And I like to just maybe save me a little. Boy, that's a great word, a great phrase. Save just an itty bitty amount of time by going ahead and finding out what that number is so I don't have to just calculate it twice. So omega AB we found to be 1.5 radians per second, and the length of AB was 2.828. So if we take the 1.5 and square it and go and multiply it, and we end up getting a 6.364 feet per second squared. So coming back down to here, we'll use that 6.364, and we only want to take the sine of 45. Obviously, because it's 45, The sines and the cosines don't matter, but I want to try to keep straight why it's the value that it is. So from that, we can find the acceleration of the angular acceleration of AB, which is now going to be, let's see how we're going to do this. We're going to multiply that by a cosine of 45. And that ends up, ooh, this is interesting. This is weird, huh? That is going to be, ooh. I think if there's a physical reason for that. That ends up being 4.5. So when we come and bring it over to the other side, it's going to cancel it out, so that that's our conclusion, is the angular acceleration is 0.
Wouldn't you divide the 4.5 by the product of the 2.828 and the cosine of 45 before subtracting?
Say that again.
So to get alpha AB by itself, you'd have to divide by 2.28 and the cosine of 45. Wouldn't you divide by those before subtracting?
Yeah, but it's going to be, you're going to divide both of them by that.
Oh, okay.
You see what I'm saying?
Yeah.
So even when it's there, it's going to, either way, they're going to end up canceling out, because I'll make this clear. This ends up being 4.5 right here. So when it comes over to the other side. So that's what we've learned here. And so even when it comes to the x direction, what we're going to find as part of this, interesting, that we're going to have the acceleration of, and maybe I'm going to write it as positive, acceleration of A, and you could call it either way, right? This is also equal to the acceleration of A with respect to D in the tangential direction. This right here, but I'm going to call it acceleration of A in the x direction is going to be equal to the acceleration of B, which we know is 3. Is that right? No, 9. Right, all the way back up here. Right, that's acceleration of B is 9. And then this one right here doesn't play a part, so the tangential doesn't play a part. I'm just going to write it out there because whatever. But we knew as drawn it was negative, but we went ahead and stuck it back in there anyway. And then sine of 45, it's kind of pointless. But then this guy right here does play a part. He's going to be plus 6.364, and that's going to be cosine of 45. So the acceleration of A in the x direction, and I think I just figured out why this thing had because I believe its angular velocity is going to be at its maximum, therefore its angular acceleration is going to be 0, because it's at that 45 in the orientation of the thing. Okay. That kind of makes sense. So we take that. So actually it should be 6. That should actually come out to 4.5 as well, right? So it's just going to be 4.5 plus 9, which I just screwed up. So it's 13.5. So they didn't ask us this, but that could have been the question, was what is the angular acceleration of link AD, and we can find that from up above where we drew the thing out. Well, I can write it up again because we didn't do it here, but now we know the acceleration in that direction, and we have the acceleration in this direction, so that's going to be acceleration of A in the x direction, acceleration of A in the y direction. So we could find what the alpha AD is going to be, That's just going to be the 13.5 divided by 2. So 6.750 radians per second squared if we were looking for alpha AD, but we're not. But in terms of the answer right here, the acceleration of A as a magnitude is the square root of, what did we get up above? We got 4.5 squared plus 13.5. That's supposed to be a 13 squared. So 4.5 squared, 13.5 squared plus square root. So we get 14.23 feet per second squared. And then the angle of that, which I'll just call theta, but probably should give it some kind of name that's identifiable. We're just going to take rise over run. So that's going to be the 4.5. Divided by 13.5. So we get an angle 4.5, 13.5 divided. So we have 18.43 degrees. So our answer is the acceleration of A is equal to 14.2. Let's give it 4 sig figs because it's the first number is a 1. And our quadrant will be down there of 18.43 degrees. That's a long problem. Usually the must ones, I bet he does it in like one step, like 3 steps. His solution. I don't know why, but there's a tendency for many professors to just take when they post his solution to make it look really easy, in a way that like I don't think a student would ever be able to like recognize and see what they are. So I never wrote down what year, what corresponding, so I'd have to search through several of these to see what his solution in his solution manual would be. But I guarantee you it's something that's really fast, right? So these are all.
But do you think that he gives more time for his students? There's no way he gives his students 3 problems like this in an hour, 15 minutes.
I don't know. I bet he does.
That's a lot.
Yeah, I know. I'm not gonna lie to you. It's just kind of nature of the beast in some ways.
He doesn't have recent stuff. He's old.
So there's one that I think this would be exam 3 for the maybe exam 2. I think he did rigid by Some of these he says pick 3 problems. Yeah, this is all one exam. There's even a chance this is a 50-minute exam now. Just some professors just don't give it. They're like, no, I don't care. Do it fast. I bet it's one of the, I could have sworn it was going to come up from there. All right, it'll be the last one. No, but that one's pretty long. That's just a tough problem. Every time you do one of those ones like that right there. Yeah, so I don't know. I didn't see it. Don't know where it is in there. Don't want to waste any more time. But it's good. This is a great resource to have, right? To be able to look through there and see.
Thank you very much. All right, no problem. Want to take a look at some more? What do you want to do? We're going to do. Sometimes we do angular the angular ones. Let's see what is this guy here? The kinematic ones. There you go. That's a good problem. Gotta mix things up a little bit. That one, where'd you go? Catman Joe. Oh, that was not even on here. Oh, no, it is right there. All right, so, don't be sad. This will make it better, people. It's a heart clap. Dynamics is hard. It ain't easy. All right, so this disk is originally rotating at 8 radians per second, is subjected to a constant angular acceleration of 6 radians per second squared. Determine the magnitudes of the velocity and the n and t components of the acceleration at point B just after the wheel undergoes 2 revolutions. So can you think your way through this problem, is the question. Do you know what to use on the equation sheet to do it? No? Maybe? Like another equation? Thank you. Print it out. Just for you and everybody else. Well, let me write down the problem. We'll see if I can read it. Very, very small. My version's very, very, very small. So we'll draw this thing in here. And we have this point B. And there's point A. I don't know why we have it at point A, but there is one. Aren't we looking for it at B? Yeah, sure.
Is the radius.
I gotcha, but like it says, oh no, he just wants the n and t components. Okay, cool. And so the radius, okay, I guess this is 2 feet, but we still didn't really use it for anything. This is 1.5 feet, that distance right there. And we're saying that the initial angular velocity is 8 radians per second. And it is subjected to a constant angular acceleration of alpha, but it didn't say whether it was, I guess you just have to assume it's in the same direction. As I said, acceleration and not deceleration, but it's nice to be able to know for sure. And we want to find the acceleration of B in the normal and acceleration of B in the tangential at delta theta equals 2 revolutions. So what equation should we use first?
Find the velocity first.
Yeah, let's find the velocity first. So what's the angular velocity at after 2 revolutions? Use the magic word constant in there, right? Constant angular acceleration. You can't barely read that. I can barely read that. It's okay. Don't call it a W.
That one squared.
Look at Eddie smiling.
What is it?
It's omega.
Omega. So
Yeah.
omega squared.
I need to get you into a fraternity. So we need to get you into a fraternity. As we used to joke, people used to joke is like, I don't need to buy my friends. That's what they would say about the fraternities. Right? alpha constant, then the angle minus.
This one.
Yeah, that one.
And we want to turn those 2 revolutions into radians.
Yeah, so it's not the right one.
Yep.
Nice.
So we can find omega squared is equal to omega naught plus 2 alpha delta theta. And noticeably that 2 revolutions, each revolution is 2 pi, so that's 4 pi. So we can find omega is equal to the square root of 8 squared plus 2 times 6 times 4 pi. So we could even do that in our heads, 64. And then 8 times 6, 48 times pi. Delicious pie. And if I did it right, which there's no certainty that I did because I took shortcuts. And when I take shortcuts, I just know myself too well. I mess things up. But you too can attempt to find the numbers. So after 2 revolutions, that's the angular velocity. So to find the tangential velocity, tangential acceleration, excuse me, we take that alpha and multiply it by the radius, that radius of b right there. So we had 6 times 1.5 feet, and a normal, but I think I could say that's 9. Are we okay with 9? Yeah. And these are feet per second squared. And the acceleration of b in the normal direction is going to be that omega squared times rb. So it's the 14.66 squared times the 1.5. Can't do that in my head. Boom. Boom. We get, if I did it right, 322.2 feet per second squared. So that's actually the answer. But if they had given us, well, that would make it, no, that would have been okay. If they had given us like this orientation, we could have got like the magnitude and direction. But so if they had told us this angle right here, because it was 2 revolutions, it would end up in the same spot. If they had given us that angle, we could have gotten, well, gotten a magnitude anyway. And then, so I might even say find the magnitude of b right there and find a square root. But it's actually not going to matter. It's that because that's one's so much larger than that one. It's not going to really contribute any, which is I've always found is like this annoying thing as a writer of problems. They go, yeah, it didn't even matter how much that one was. So you can't even tell if a student got it right or got it wrong by way of looking at the final answer. There's this 322.3 feet per second squared because this one's so much bigger than that one. You couldn't even tell if they got that right. But I won't sing you the blues. Sing you the blues about my troubles, my problems.
That was a much quicker question.
It was. If I could find 3 of these that demonstrated your ability to solve a problem, a complex problem, I would do it. But
see, you don't have to demonstrate your ability to solve a complex problem, just a problem.
Trying to get your mind, we're trying to get your mind to like it could break stuff apart.
You're trying to break my mind?
No, I'm trying to see, trying to get your mind so it's able to break stuff apart. If in the process I break your mind, it's just like a side benefit for my Schadenfreude. You know what Schadenfreude is?
I got nothing out of that sentence.
You know what Schadenfreude is? It's pleasure through other people's misery.
You enjoy that, don't you?
I do not. But I had professors that did.
What if it's my misery?
Did you hear that pause? You hear that pause? No, it's not true. I care about you and I want you to succeed. I feel empathy. I am not a sociopath. Say that really loud just to try, it's one of those phrases, if you say it, the louder you say it, the less it seems true.
You're convincing yourself. The more you say it, it's just.
There's got to be, must be. Let's do more problems because more is better. I've been told, except for pain. I have some really difficult ones. I decided not to use those. I decided to go with our good friends at the Missouri University of Science and Technology. I want to visit there sometime. Really?
He plays golf. He's a mechanical engineer.
I did not even know of its existence except when like old dynamics exams. I Googled old dynamics exams and I searched the world over to try to find the place. And I'm like, this is a great repository. It's not as good as Purdue.
You Penn State stuff too, right?
I tried. No, there's one that's great. There's one that's great, and I have mentioned this before under useful links and resources. There's a freaking genius at one of these. I'm not sure if it is. I don't think it's Purdue. I think I have the university wrong. I will see it right away as I go there. I think it's Washington University in St. Louis.
One of my good friends is engineering there.
Really?
Yep. On scholarship.
This one dude is nuts. I think it's Potter. This guy is like, he just wants to see if he could make people laugh during an exam. That's his goal. So he like does things with Captain Underpants, and he tells a story.
Oh, look, he drew a merry-go-round.
Yeah, there's a couple of crazy ones. There's like a final exam one where I just think he's just burned out or something. And so he goes, Obi-Wan attended Hughes a carnival this year, and his favorite ride was the roller coaster. And he just tells his long story. And some of them are like continuing stories right there, where he's using the Force. And there's Luke, and this guy. I just want to meet him. I tell you what, I want to hang out with this dude. This guy, he gets like a theme going, and he won't let it go.
Oh my God.
Kylo Ren, yeah. You want to find the instantaneous center of rotation here. Find the instantaneous center of these bars right there that makes the walker go.
That's crazy.
Do you think people fail this class with a smile on their face?
Yeah. Are his problems hard? Have you done any?
Oh yeah, I've done somebody. Well, here you go. He does this. You write out the solutions for it. You can see, bang, bang, boom.
At a quick glance, it doesn't seem that bad. A very quick glance.
Yeah. Here you go. Here's the impulse and momentum problem right there. No, actually, that's a work problem. That's a work problem. Sorry, work energy problem. So anyway, let's get back to the thing at hand. Let's find ourselves another problem to do.
Were you recording this?
It's all being recorded. Why are you questioning whether it was a good idea to record it or to say any of the things that I've said during it?
No, I just didn't know it was being recorded.
Sure. It's okay. I won't be offended. Even though it might sound like I was offended. Let's do this one's harder. Let's do a hard one. Although I think if I'm looking at this right, no, this is a little more challenging. This one, yeah, he's hard. So let's do him. Let's you do it this time, because you get more benefit if you do it instead of watch it. Let's see, which one is this? Let's see, where'd you go, Catman Joe? I think I said that already today. I just shouldn't say it again. There he is, number 4. So a 1 foot radius disc, AB, turns at a constant angular velocity. Wait, is it constant? Oh, I don't like that. I want to go a harder one. I misread it. It's too much like the other one. I think, maybe. It's also got a 45 in it, so I'm changing my mind. Ooh, I like this one better. Okay, so you want me to do it because you already drew it?
Anyone else ready to go?
Can you do the other one?
What's that?
Can you do that?
You want to do another one? Different one? You don't want to do this one?
Guess we're doing a
If it's
different one.
similar to the one that-
If it's similar to one we already did, there's no reason.
Yeah, just do.
But I did see one just a second ago that I thought, oh, that might be good. But then I changed my mind. I thought maybe this one, but I think what he did, I suspect what was done here, I saw the acceleration in there, and I think what he decided to do was to give you, and that's actually pretty common right there, to give you the angular velocities to speed the thing up, right? So ask you an acceleration question. And so we want to find the angular acceleration of probably both of the links right here. So that was a problem there. It's like, okay, well, it turns it on its head just a little bit of a difference. Still hating the 45 thing, by the way. Just don't like it. Don't like 45. It doesn't. Well, because you're not demonstrating that you can identify which angle goes with which angle, with what part. That you could make a bunch of mistakes and still get the right answer. And no, it's not. It's the opposite.
Does anyone agree with that?
Of course.
I mean, it's good for us.
Yeah, it's good for you, but it's not good for, it's good for your grade, but not good for the demonstration that you've been able to like think through the problem and not.
Thought enough through it if you were close enough.
That's not the, sorry, I had to, trying to be respectful. I just respectfully disagree there. But my problems aren't your problems. I got it. But your problems are my problems.
You give us problems, so we solve them.
That's the transaction we're doing, yes, you're right. I really want to meet that guy Potter at, if you do have someone who knows someone who's going there, tell him I want to meet that guy.
I'll call him, see if he does.
Give him my email. I'm gonna go out on a play date. Do you remember saying that, the play dates all the time? You go, they went on I just thought it always sounded like, this seems a little weird to me. Why am I sending my son on a date? I don't know. I can see that. So one of my son's friends, when they were little kids, his name was Tucker, and I think it was in first grade or second grade. I don't know. He had to be old enough that he could write this. And anyway, you were like the kid of the day, and you wrote down stuff you wanted everybody to know. And he wrote, "I went on a play date with Tucker, but he did not spell Tucker." And the teacher sent a picture of it to me. Dying and laughing with his big grin on his face. So it's one of my prized possessions. Turn around. I went on a play date with him. All right, cool, man. Big grins. All right, so the results of this, they tell us that this was 10 radians per second, and this also was 10 radians per second, so that we didn't have to do the velocity analysis, even though it was probably pretty easy, because once again, on this one, the ICR, if you haven't noticed, would have been right there at A, right? We're all in agreement with that? No? Yes? Okay, cool. So that's the reason why we had the 10 radians per second the same in here. So now we want to do the acceleration analysis, and I'll try to find, maybe I don't know if it's worth my time, try to find all the solutions and put them up in there together, but I'm like, you could do it too, you could do it too. That's a funny words, funny voice I just used. All right, so, okay, so one of the things we could do is, I'll probably jump over to link AB and find it's the normal acceleration that's going to be taking place right there. That acceleration of B with respect to A, and the normal direction is going to be the omega of AB squared times the length of AB. which is just going to be that 10 squared times 0.2 meters. So that should be 20, right? Because we're going 100 times 0.2. Wow, math. And we don't quite know what direction the other acceleration, the tangential acceleration, is going to be. But we could do the acceleration of bar BC in 3 diagrams. Because we know this guy is going, this AC is going to be equal to 1 meter per second squared. And we know this guy right here, we call this acceleration of B in the y direction. And I really wish I had left more room over here, but it's okay, we'll survive. So I'm going to use C as my reference because I know the entirety of his thing. I don't know that it's a he, by the way. And we could pin it right here. And all right, so we're going to have a component of acceleration in that direction. We know that that's 45 right here. And so this guy is going to be the acceleration, still on the screen, of B with respect to C in the normal direction. And I'm going to guess, an acceleration of BC that's in that direction, and therefore this is going to be there's 45 right there. This is the acceleration of B with respect to C in the tangential direction, which we know is going to be the alpha BC of L BC times L BC. We never found L BC. Let's get him over here somewhere in the geometry. Should be able to do this in my head, probably, but ain't gonna. 0.2 squared times 2 squared, yeah, 0.2828 dar. And I'm losing room over here, so I'll write it over here to this guy. In the normal direction is omega BC squared L BC, or 10 squared times 0.2828. I think that's 28.28. I'll go ahead and write. No, I already over there, so that's good. Good enough. So anyway, writing on an equation for this guy right there, the one that we want, it's the acceleration of B is going to be equal to the acceleration of C plus the acceleration of B with respect to C in the tangential direction plus the acceleration of B with respect to C in the normal direction. And because we know stuff in the y and we don't know it in the x, we'll go in the y direction first. the acceleration of B right here in the y direction is going to be this guy up here, that 20 meters per second, and it's positive. So 20 meters per second. And then we look over here, and the acceleration of C in the y direction is what was given, and it's a -1, right? Because it's this up here that gave us the acceleration was 1. And nothing else. Over here in the y direction, we're going to have positive with our guess of alpha BC times our 0.2828. And remember that's, we only want to use the part that's in the y direction, so it's got to be the cosine of 45. And then we also need to include, and he is in the positive direction, the acceleration of B with respect to C, which you have as 28.28, but again, only in the vertical direction, so we take the sine of 45. And now we're going to be able to get alpha BC. So we're going to add 1 over to this side, that makes 21. And then we're going to take our 28.28, multiply it by a sine of 45, probably is going to be 20. We're going to subtract over to there. That was interesting, right? So that became 21, but now that this becomes 20 right here. That's okay. It's going to be just 1. And now divide by 0.2828, and then divide by a cosine of 45. And we get a 5 with a bit of change on here. I'm guessing that's round off error because we used 0.2828 and it had numbers that kept going on right there. But that's the angular velocity, angular acceleration of BC, radians per second squared. And now we go continue in the x direction for what we were doing. Get to fall off. X direction. Bomb, bomb. And let's see. This one right here is we don't know this. Acceleration of B in the x direction. Maybe I'll just draw that on there. Acceleration of B in the x direction. Try this positive. Oh, by the way, let's see. Double check. Yeah, this became a positive direction, so we actually guessed the correct thing, right? So got to be careful with that. I believe we got it right. So the acceleration of C has nothing in the x direction. So we come over to here, and we have, so we knew that this was correct. So it's positive, and it's got an alpha of 5,001 because I'm just stubborn. 0.2828, and remember that has to be, now it's going to be the sine of 45, and now this one's going to be negative, and it's that 28.28, but the cosine of 45. So the acceleration of B in the x direction. Let's see if it doesn't do something weird by canceling out 0.2828 times, and then 45 sine times. So this all becomes 1. That times that times that is 1, apparently. And then so 28.28 times the cosine of 45 becomes basically 20. So you subtract the thing out and you get a negative, what looks like 19, but 18 point, yeah, it's gonna be 19 because it's 8, I got 18.9996 or something. So 19, negative 19. And these are meters per second squared. So apparently it is actually going in the, accelerating over in that direction. So back up to, we could redraw it or come back up to, yeah. Drawing this thing again. So now we know it's going in that direction. And while I'm here, I'll put this on there. So here's the acceleration of B, the X direction, acceleration of B in the Y direction. So here is our alpha AB. And so alpha AB should be equal to AB X divided by L AB, or 19 divided by 0.2. And that becomes a alpha of 94.98. Really 19.2. It's really 95. But 95 radians per second squared. And it's going to be clockwise. So the answers are alpha BC is equal to 5 radians per second squared counterclockwise, and alpha AB is equal to 95 radians per second squared. And I would say this is pretty representative, I think. But this would be the longest problem on an exam. Probably worth this is probably a 40-point problem. I would suggest that like you make sure that if you don't think if you're really concerned about time, make sure you get all the diagrams. I put a lot of stock on diagrams that you're showing me that you got your orientations on things, right, onto the thing. I see a lot of packing up. I'm ready to pack. I did another review session this morning, so I'm already kind of burnt. It was also there weren't any people there. Like, I mean, that we'd already decided to do it remotely for my ME370 because we couldn't get more than 2 people together out of the 7 people in the. So we decided it was going to be online, but I really don't like the online stuff. Thank you.
Almost do it 5:30. Thank you.
Yeah, I think so. I think I had that done during our regular time. It was negotiated. It was negotiated that way.
Yeah, I was just hoping it was midnight because I
I have the late's midnight, and then here's a secret. I don't think I've taken off with someone being late yet. Or maybe I did once early on. They teach you in leadership class. At least they did back in the day when I had to take a bunch of leadership classes. Is you got to be a hard ass in the beginning, and then like ease up as you go along. Because if you're like easy in the beginning and then you try to have to be a hard ass because nothing's going right, people really hate your guts. You'll lose your followers. I've watched a lot of people where they just like total hard ass in the beginning, and then they start getting they're following that. Anyway, do what you gotta do. Thank you. Have a great weekend for the best you can, and let's stop recording.